Oh crap, I started in the wrong place. All right, let's try this again. Hey, let's start over. This is me going through our homework for chapter 1 and 2. You've got these slides that I'm showing to you right now in front of your face that you can look at separately without my voice if that's annoying. But there's going to be a couple of them that'll be computational that I thought it might be useful for me to walk through with you. And so I'm going to do that. I'm going to try and produce one of these little videos for every single one of our homeworks. So let's go ahead and jump in and not waste any time. I'll just sort of talk through each one of them. These are pretty simple and straightforward in these first few chapters. First question that you're, oh, nope, that's not even a question. This is a reminder. uh, this will come up in the future. Where is the skewed tail? We went over this in class, but just thought I'd give you one more pass at it. It's a positive skew if the fat tail that is longer than usual is going in the positive direction, like you see on the left. It's a negative skew if the fat tail that is longer than expected is going in the negative direction, like towards 0. If you imagine this as being on like an x-axis, you can see the difference between positive and negative skew there. That's just something to remember. That's not even one of our questions right now. Just something that enough folks struggle with that I figured I'd give it one more pass. Okay, let's take a look at number 12 on chapter 1. You are giving examples for the different kinds of variables that we've got in A, B, C, D, E. And you don't have to come up with the same example as me, obviously, but it should be something that fits into the category, and hopefully you'll be able to see whether or not you're barking up the wrong tree or not based on the examples that I give. So equal interval, your numbers are equal distances apart. Their intervals are equal. An example of that is temperature, whether you're talking about Fahrenheit or Celsius. There's the same difference in heat between 0 and 1 degrees Fahrenheit as there is between 99 and 100 degrees Fahrenheit. So that is equal interval, right? Rank order. It just, where are these numbers in relationship to each other? They are put in order, but the distances between those ranks are not necessarily equal. There's no evidence that we know whether those are equal or not. So U.S. college rankings, U.S. News college rankings, which is a total scam, by the way. Like, don't pay attention to college rankings. They don't mean anything. Other than who's spending the most money and paying the most attention and buying the most ads in U.S. News. Anyways, we have no evidence that it is the same distance between Duke and Dartmouth as it is between UVU and SLCC, presuming that those colleges are next to each other in rank order, which I have no idea. But you get the idea there, hopefully. Nominal, which I always tend to call categorical, but it's the same thing. Nominal variables, all of your values are categories, they're names. So marital status, married, not married, divorced, widowed, right? These are different categories and you belong in a category. But they don't necessarily have any order to them. There's not even really any numbers attached to them. They are just categories. And then ratio variables are equal interval variables that have an absolute 0, where 0 is an absence of the thing being measured. So height and weight are good examples of that. Something that has 0 height is probably not a physical object, but it is at least not a three-dimensional object. That is an absence of height, absence of the thing being measured if you were at 0, right? Okay. And then even though this isn't quite the same kind of categorization as the other variable types that we're talking about here, a continuous variable, well, let me just mention, a continuous variable is going to be either interval or ratio, right? So continuous and discrete only apply to those two types of variables. A continuous variable can assume any value along the possible range of values. Again, height and weight are good examples of this because depending on how specific you want to get with weight, you can weigh by pounds or by ounces, or by grams, or by milligrams, or nanograms. So depending on how specific you want to be, you can have any number along the range from 0 to infinity when you're talking about weight. So okay, great. That's all we need there. Number 13, we've got these values, and you're given a data set and asked to make a frequency table and a histogram out of them. And so you can see I have done that on this page. I've just given you sort of the outcome of this rather than walking through it because it feels pretty simple, right? You just count up how many ones you've got, how many twos you've got, how many threes you've got, and on down the line. You are going to end up with a total number of scores that is, let's see, how many have we got? 8, 16, 20 scores. So you just list all of the values, making sure to not skip any just because you don't have any values attached to them or any scores attached to them. That isn't the case this time, right? Every single value has at least a couple of folks that have that score, right? So you just count up your ones and your twos and your threes and your fours and your fives, and that become your value and frequency columns. Don't forget to do your percentage column by taking that frequency and dividing by the total number of your frequencies. So if I add up all of my frequencies, I get 20. So 2 divided by 20 is going to give me the percentage of 10. So 10% of this data set is at a 2. 4 divided by 20 is going to give you a 20%. And so 20% of my scores are 4s, 40% are 8s, and on down the line. And then we stick that into a histogram. Remember, with histograms, your bars should be wide and touch each other. And so you have your y-axis as the number of people that have that score that are along the x-axis, right? So the value of 1 is on the x-axis. You've got 2 people who have 1s, and so your bar is too high. You've got 4 people that have 2s, and so you go up 4. 8 people that have 3s, so you go up 8, and on down the other side, right? Hopefully that makes sense. And then last but not least, describe the shape of this distribution. It is unimodal. Our mode is 3. That is the most commonly occurring number. It is symmetrical in that if you were to split this right down the middle, it would look the same on both sides, right? It does look the same on both sides. And it is also normally distributed, which for right now, I mean, if you didn't put normal here, that's okay. A normal distribution is perfectly symmetrical. It is possible to have symmetrical distributions that are not normal, but don't worry about that distinction for right now. We'll get into normality next week. Okay, this is a big data set. I am sorry for that, but once again, we are creating a frequency table. So once again, you have to have to list all of your values, and it tells you to start at 0, if I remember right, and go up to the highest number you've got is 34, so we can stop there. But you don't want to skip out on any numbers just because they have a 0 frequency, right? So you get everything from 0 to 34. That makes it a pretty long table, but that's okay. That's what you're asked to do here. And then you just go through your data set and cross out each number when you come across it. Oh, we've got 1, 2, so I'm going to put a frequency there. 1, 6, 1, 11, and on down the line we've got 3 22s, 2 18s, 2 19s, and so on. And once again, all you got to do is just add up your total frequencies, which, let's see, what have we got here? 1, 2, 3, 4, 5, 6, 7, 9, 11, 12, 15, 17, 18, 19, 22, 23, 24, 25? I may have miscounted that. No, that's right. Okay, so we've got an N of 25. That's our sample size. And so for each frequency, I'm just going to divide the frequency by total N. So 1 divided by 25 is 4%. It's 0.04, right? And on down the line. 2 divided by 25 is 8%. 3 divided by 25 is 12%, and so on. And so that's what your frequency table should look like. Now, if you are going to make a grouped frequency table where you're looking at ranges of values, it should look like this, where once again, it tells you to, if I remember right, to break them down into these ranges, right? Where you've got essentially 5 values in each range. And you just count how many people you've got in that range, right? So if I wanted to know how many people I've got in 10 to 14, I can just look over here, right? I've got 0 at 10, 1 at 11, 0 at 12, 1 at 13, 1 at 14. So I add up those 3, and I have a frequency of 3 in that range. I am still, when I do my percentages, going to divide by 25 because that's still my frequency. But I am just giving the percentage for that range rather than for each individual value. Number C, I've actually got on the next slide, so let's pop over there. And it should look something like this, where, again, you are giving the ranges on the x-axis rather than the values. Again, you may occasionally see, either in the textbook or elsewhere, a grouped histogram where you get the midpoint of each range instead of the range itself. I find that less informative. I don't like to do it that way. But if you were to do it that way, what is the middle between 0 and 4? I want to say 2, but I think that's, so I think you'd have 2 and then 7 and then 12 and then, or maybe it's 12.5. Anyways, you see why I don't like to do it that way? Because then I have to do more math. Anyways, that's what your grouped histogram should look like. And bumping back to the previous slide, what is the shape? It is negatively skewed because we've got a longer tail going towards 0 than we do on the top side. And also, it is multimodal. Now, you might ask, I just see one spot that's higher than the others. Shouldn't that be unimodal? No, because you've got multiple value ranges that are all at the same height. So even if you're looking at it in a grouped frequency situation, you have equal frequencies in this range, in this range, and in this range. And so that's actually 3 modes. So it's multimodal rather than a single one. Worth recognizing and calling out for yourself that if this were an ungrouped histogram, so if we had a bar for every single value, it would be unimodal. Because nope, I'm lying. Sorry. As I'm looking at this, as I'm looking at my frequency table, we've got 3 at 22 and 3 at 28. So it would still have more than a single mode. You might call it bimodal, because those two are your most commonly occurring values. But you would describe that ungrouped histogram differently than this grouped histogram because it's going to look different, right? You're going to have 2 peaks instead of 3 that are all right next to each other. Okay, hopefully that made sense. Okay, once again, I'm giving examples. You do not need to come up with the same example, but these are hopefully demonstrative. A bimodal distribution, it is anything where you have 2 values that are most likely to occur, that have the most number of scores. So speaking in general terms, number of car accidents annually by age group. So if you're grouping together teens and the very elderly, those are going to be your 2 most likely groups to get in accidents, and probably at roughly equal rates. Ages of attendance at a Dua Lipa concert. I just picked a female artist that I assume that young teenage girls like. I don't know. Ariana Grande? Sure, whatever. You get the idea. You're going to have a bunch of folks who are 13, and then a bunch of folks who are 46 or whatever. And again, are those true modes? Well, if you're looking at each value separately, maybe not. Maybe one of those groups is larger than the other. But if you're just looking at your distribution from a distance and sort of looking, do I have two big peaks? Yes, in this situation. So we're talking roughly bimodal, not perfectly bimodal. Something that is approximately rectangular. I gave you the example in class of different class rankings at UVU. You've probably got an equal number, roughly equal number of freshmen, sophomores, juniors, seniors. But also the probability of rolling each number on a 6-sided die, or 20-sided die for that matter, that they are all equal probabilities. And so if you were to make a histogram of those probabilities, it would be rectangular. The number of each color of Skittles produced at the factory. I'm not sure about that one. I feel like there's always fewer red ones because those are tastiest. Are they tastiest? My mouth thinks so. Whatever. Positively skewed. Number of serious relationships during college. Most folks are going to have 0, 1, or probably 2. And then you're going to have a small number of folks that are going to have, 12 or 20 or whatever, because there's something wrong with them. Or there's nothing wrong with them and they're just really popular. I don't know. But you can see you've got most folks sort of grouped down at one end, and then trailing off in a thicker tail the higher you go, right? Number of children born to each family. Most folks have 0, 1, 2, 3. If you're living in Utah, 4, 5 are still going to be pretty high numbers. But then you go to 6, 7, 8, 9, 10, 11, 12, and you get fewer and fewer people in that direction. So you get that fat tail in the positive direction. My next door neighbor, who is turning 90 this month, had 14 kids. Bonkers. Also, she's awesome. And she's like grandma to like half of my city. So whatever. Okay. Definitions for variance and standard deviation. Variance is the average amount of deviation from the mean in squared units, right? So if you take a group of scores and you figure out how much each score deviates from the mean, and you square them all, and then you add up those squared numbers and divide by how many numbers there are, you've computed an average, right? That is your average amount of deviation from the mean in squared units. Your standard deviation is the same thing, but it's unsquared. So standard deviation, we like it because it makes sense in our brain. It's just the average amount. We're in the same units that we started in, the same scale. So it's the average amount of deviation from the mean in that set of scores. Why do we use standard deviation more frequently? Well, because it's easier to think about numbers in the units that you're dealing with compared to squared units. Our brain does not like square units. So if I were to poll the class on how many apples you ate this week, there would be some average. It's probably going to be like 2 or 3. And then we could compute the standard deviation. How much does everybody in the class vary from that average of 2 or 3, right? And if I'm talking about, let's say we've got a standard deviation of 1.2 apples, right? That means that on average, that people's numbers of apples that they ate in our class, people are on average about 1.2 apples away from the average, right? And that's easy enough to think about. But if I start talking about squared apples, what the heck am I even talking about there, right? That doesn't make a ton of sense. So that's why we like standard deviation more. That's why we use it more. Easier to understand. Okay, let me swap over to, I hope this works, my iPad, so you can see this next problem. Get out of the way. Stop. Go. Oh, wait. There we go. Okay. We've got a data set. It is a large one. We actually have 21 numbers in this data set. And we are supposed to do some things with it. First, we are supposed to compute the mean. Okay. So in order to compute the mean, I am going to need to add up all of these numbers. Not the eraser. There we go, the pen. Stop that. Stop that. Stop that. Get out of the way. I don't want to solve it. I want my eraser. This will hopefully go more smoothly in subsequent. And this is the first time I'm trying this. Okay, so I want to get my iPad to stop offering to solve things for me because I'm doing it by hand. Anyways, if you add up all of these numbers and divide by 21, you should get a 2. That should be your mean, okay? I won't do that by hand because you'll just be listening to me add things on my calculator, and that doesn't help anybody. The next thing it asks you to do, though, is to find the median. Okay, so I did want to show you this. If we've got 21 scores, I need to find, you can see I have given each of these scores, I've put them in order from least to greatest. I know I've got 21 of them, so I just put 21 ranks here and then put them all in order from 0 up to 5, right? Okay, now what I want to do in order to find my median is to find the middle rank, I do n plus 1 divided by 2, which in this case is 21 plus 1 divided by 2, which is going to equal 11. That means, oh, look, it picked it for me for a second there. I don't know why. I'm at my 11th rank, and my median then is a 2. Right? Okay, cool. Next thing I'm going to do actually is compute my sum of squares. That's what it wants you to do for C. So I've already got all of my numbers in a row here, and I am just going to walk us through all of the steps that it asks us to do. First, I want to do each score minus the mean. So let me just do that really quickly. 0, 0, negative 2, because remember my mean is 2, right? Why is it putting lines there? I don't know. I'm just doing each score, so I did 5 minus the mean of 2, and I end up with a 3, right? 1 minus 2 is a negative 1. 4 minus 2 is 2. Negative 1. 1. Negative 2. Negative 2. Negative 1. Stop that. 2, 2, negative 2, negative 1, 2, 1, 2, 0, 0, negative 1, negative 2. Okay, that's all of them. Great. Now what I want to do, now that I have, if I were to add all of these deviations, these are my deviations from the mean, right? If I were to add all of these up, they should sum to 0. Okay, I'm not going to go through that. I'm going to trust that that is accurate. The next thing I want to do in order to get to my sum of squares is take all of these deviations and square them. Okay, so 0 squared, 0, 0, 4, 9, 1, 4, 1, 1, 4. Sorry, that's a 4. Another 4, 1, and then 4. That is not supposed to be a 0.4, that is just a 4. 4, 4, 1, 4, 1, 4, 0, 1, and 4. Now, if I add all of these up, let's see, let me do this by, hopefully my brain will work. 13, 14, 18, 19, 20, 24, 28, 29, 33, 37, 41, 42, 46, 47, 51, 52, 56. That should be, if I did that properly, that should be my sum of squares, right? Now, from my sum of squares, I can then compute my variance by just taking that sum of squares, dividing by my number of scores. I am actually going to swap back over for a second to my slides because yeah, okay, so 56 divided by 21 gives us a 2.67. 2.67 is a 2.67. If I then compute my standard deviation, I just take the square root of that variance. That ends up being a 1.63, right? Okay, one last thing before I swap back over to the slides. Just please recognize that these are two sort of separate processes that I was sharing the screen on. I'm just figuring out my median over here, and over here I am doing all of the computations for sum of squares, variance, and standard deviation. And I just have a wide screen, so I figured I'd share the space. Okay, let me then hop off of this. Yeah. Oh. I'm over here looking at my. Yeah, I wrote that like I thought you were looking at it, but that's the same thing that you were seeing on your slides. Okay, I need to streamline this. Okay, anyhow, that's that question. You see all your answers there. These I will not do by hand. Hopefully you have seen me do that and can reproduce that. And hopefully with these small data sets, you can see what I'm doing here. To compute my mean for these 6 numbers, I just add them all together and divide by 6. It gives me a mean of 3.167. If I wanted to figure out my median for that data set, I just line them all up, least to greatest. N plus 1 divided by 2 will give me my rank, which ends up being 3.5. So I go between my third and fourth numbers and I average them together, right? So if my rank 3 is a 3.2, my rank 4 is a 3.3, rank 3.5 is going to be a 3.25, right? So my median is 3.25. Hopefully that makes sense. If I take those numbers, take those 6 numbers in my data set and compute my sum of squares, well, I just take each one and subtract the mean and then square it, right? So you can see I've done that for all 6 numbers. 2.6 minus the mean of 3.167, 3 even minus 3.167, 3.2 minus 3.167 for all 6 of them. And then whatever that number is, I'm going to square it and I'm going to add them all together. I end up with a sum of squares of 0.533. From my sum of squares, I can then really easily compute my variance by taking the sum of squares divided by n, which is 6. I end up with a variance of 0.089. I take the square root of my variance to get my standard deviation. Square root of 0.089 is a 0.298, and that's your standard deviation. Number 14, again, we're just doing the same sort of thing, but we've got, once again, a smaller data set. 8, -5, 7, -10, and 5. Why did I put 2 brackets around those? I don't know. I've just given you that same sort of setup with the 3 columns of you've got your X values, and then next to that I have computed the X value minus the mean, and you can see down at the bottom of the box here, I have computed the mean here. We've got an average of 1 for this data set. So 8 minus the mean of 1 is a 7. -5 minus the mean of 1 is a -6. And so these are our deviation scores, this middle column. And as you can see, they sum up to 0. And then my next column over is those deviation scores squared. And hopefully you can see how that works. I square 7, I get a 49. I square -6 to get a 36, and on down the line. And then I add those up, add up those squared numbers to get a sum of squares of 258. So this is the same thing I was doing on the iPad where I was actually drawing it out by hand. I've just done it in a little table on a computer and shown it to you. So great. My mean is 1. My median, if I were to line these numbers up from least to greatest, my least would be -10, and then -5, and then 5, 7, 8. N minus 1 divided by 2 is going to give me a rank of 3. That's going to be my middle number, which ends up being the 5. Right? So I get a median of 5. Sum of squares, I just showed you. We computed that, 258. Divide your sum of squares by your n, which is 5. And you'll get a 51.6. Take the square root of your variance, square root of 51.6, and you'll get a standard deviation of 7.18. And hopefully that'll make sense. Okay. This question might have been a little confusing just in how it was phrased, but it's asking you where are the mean, median, and mode going to be in relationship to each other on a negatively skewed distribution? This is what I was talking about right at the beginning, and what's positive skew, what's negative skew. Remember, the negative skewed distribution has the fat tail to the left, going towards 0. So where are those 3 central tendency numbers going to be on that distribution? Well, the mode is going to be right at the peak, because the peak is the mode. That's the most commonly occurring value. But then the median is going to be pulled a little to the left of that, a little towards 0, because you've got more of the numbers off to one side because you've got that fat tail towards the left, right? And then your mean will be pulled furthest towards the negative direction, where it's, in fact, let me just draw that out for you really quick. Hopefully that will make a little bit more sense. Okay, so this is a negatively skewed distribution. I'm so bad at that. Hopefully you can see, even though that's, nope, can't do it. Sorry, put up with me for just a second here. Okay, so here we're going to get a fat tail. Okay, that's a negatively skewed distribution. Your mode is going to be right here. Your median is going to be to the left of that, because you've got more scores on this side of the distribution. And so the 50th percentile is going to be a little to the left of that peak. And then your mean is going to be pulled furthest to the left, because the mean is most influenced by these outliers way out here, right? Okay, that's all I wanted to show you. That is a question that will show up sort of pretty much more or less in that exact same format on the test, and you'll be asked to sketch it out. Oh, I'm an idiot. It's right here on the slides. Okay, I'm done. Thanks, everybody. Hopefully this was helpful.